So we'll look at this, where magnetism comes from at the microscopic level. Okay. You guys all know the model of an atom. Okay, so here's the nucleus. Oops. Okay. So this is a lithium nucleus. Okay. Now, so it has 3 electrons in the model. Is these electrons go around the nucleus. The nucleus is tiny. Of course, this is not to scale. And let me remind you of the dimensions of the atom: 10 to the minus 10 meters, and the size of the nucleus is 10 minus 15 meters. Okay. So if I drew this to scale, I wouldn't be able to show you the nucleus. All right, so we saw that the electrons go around the nucleus. In this chapter, we just learned that moving charges produce magnetic fields. Okay, so if these electrons go around, they must produce a magnetic field. And so a minute ago, Ty was saying something like this is an electromagnet. This guy produces a magnetic field, okay, all around it. So these electrons going around is like a loop of wire and should produce a magnetic field. So let's see what kind of magnetic field will it produce. Okay. So here's an electron going around it, and it turns out that the magnetic moment of this electron is I times A, the current times the area of this loop, and it can be shown to be that related to the angular momentum. In atoms, things are quantized, so the angular momentum is quantized, and the value of this angular momentum due to the orbital motion is square root of L times L plus 1 h bar. E is the charge of the electron, me is the mass of the electron. Okay. This is the angular momentum of the electron. Okay. Now, let's, okay, so the angular momentum of the electron is h bar. Okay, so L can take integer values. L equal to 0 corresponds to the s orbital that you hear in your chemistry classes. L equal to 1 corresponds to the p orbital. L equal to 2 corresponds to the d orbital, and so on. So those are the orbitals. So for the s orbital, L is 0. The angular momentum is 0. So the s orbital, if you think of it classically, it's just a cloud, and the electron is not going in a circle, it's going back and forth like this. Now that's not a good way to think about it, but that's roughly the translation. So in the s orbital, it has no angular momentum. All right. Anyway, so we mentioned a whole bunch of things. Okay, so in an atom, each electron circles the nucleus in about 10 to the minus 16 seconds. Okay, so if you thought of it as a current, the electron travels quite fast. This would produce a current of 1.6 milliamp and a magnetic field of about 20 Tesla at the center of the circular path. So this electron moving about should produce a 20 Tesla magnetic field at the center. One little electron. Okay, again, let me remind you, 20 Tesla is a very strong field. In an MRI machine, you have a 2 Tesla magnetic field, and some of the strongest fields we've produced is about 100 Tesla. So here's one piddly little electron producing a 20 Tesla uh, magnetic field. So how come we don't feel all these strong magnetic fields? What gives is the question. Okay. So here's the thing. In most materials, because of oppositely moving electrons, magnetic effects produced by the orbital motion is zero or negligible. So let's go back to this model. So what we are saying is, so if you have multiple electrons in an outer shell, say, if this electron is going in this direction, that'll go in the opposite direction and they'll cancel each other. So orbital motion. And if there's a single electron, it's in an s orbital, and then its magnetic moment is zero. Okay. So that's what happens. So in an atom, most of the orbital motion is the magnetic moment. In most materials, because of oppositely moving electrons, magnetic effects produced by orbital motion is negligible. But it turns out that the electron is spinning as well. So, and that's a moving charge, and so that acts like a magnet. Okay, so if an electron is spinning like this, its magnet is pointing in that direction because of the fact that it's a negative charge. And the strength of this magnetic moment, it's given a special name, Bohr magneton, after Niels Bohr. The Bohr magneton is given by EH bar to ME. ME is the mass of the electron. And so the strength of this magnet, the spinning electron is like a magnet, and the strength of this magnet is 9.27 times 10 to the minus 24 joule per Tesla. Okay. All right. So the magnetic moment due to this spinning electron is that. So here's an interesting thing. So the magnetic moment of some atoms and ions. So here's a hydrogen atom. Okay. So here's the hydrogen atom. Okay. An electron going around it. And it's the magnetic moment of this entire atom is 9.27 times 10 to the minus 27 joule per Tesla. Okay. The same as the Bohr magneton. Okay. So what we're saying is the magnetic moment of this atom is the same as the magnetic moment of the spin of the electron. So the hydrogen atom acts like a magnet whose magnetic moment is coming from the spin. And so for helium atoms, there are 2 electrons in the spin point in the opposite direction. So the magnetic moments of all noble gases is 0. Okay, so that's, okay, so for the entire atom, the moment is coming from the spin. Okay. Atoms with odd number of electrons generally have non-vanishing moments. Okay, so they act like, when we see moments, meaning they have a non-vanishing magnetic moment, they're magnets. Magnetic moments of atoms is a vector sum of the spin and orbital magnetic moments. Right. Now, we won't, okay, now I just want to quickly define some terms. Some of you who are going to be material science engineers will find this useful. All right, so we'll talk about magnetic properties of materials. And from a magnetic perspective, you can classify materials into 3 kinds: ferromagnetic, paramagnetic, or diamagnetic materials. Ferromagnetic materials have strong magnetizations. Okay, so there are materials from which you can make strong magnets. And paramagnetic and diamagnetic materials are, if you put paramagnetic material in a magnetic field, it'll acquire magnetization in the direction of the magnetic field. Okay, so let's so a ferromagnetic material it has strong magnetization. Okay. It can have strong magnetization. If you have a paramagnetic material, you put it in an external magnetic field and it will acquire a magnetization. A diamagnetic material, you put it in a magnetic field, external magnetic field, and it will acquire magnetization in the opposite direction. Yeah. So paramagnetic and ferromagnetic materials have atoms with permanent magnetic moments. Diamagnetic materials are those made of atoms that do not have permanent moments. Okay, so ferromagnetic materials. So here's a sample of a ferromagnetic materials. You can see those little grains are domains. And what this diagram is showing you is in a domain, all the individual atoms or magnetic moments are lined up. Okay, but you see the domains themselves are randomly aligned. So this bulk sample won't be magnetic. Now, if you can somehow get these domains to line up, then you can make a strong magnet. The more lined up they are, the stronger the magnet. Okay. And the way to do this is, for instance, like this. So here's a material where the domains are all randomly aligned. You wind a wire through them around the material, passes strong current, and what will happen is the domains will line up. And once you remove the current, now you have a strong magnet. Okay, so that's ferromagnet. By the way, so domains have volumes of about 10 to the minus 10 meters cubed and about 10 to the power of 20 atoms. So this thing has a very small volume. It's roughly the size of a grain of sand. Okay. All right, so we'll define some terms that, again, material science engineers will find useful. All right, so let's say you have a substance, you place it in an external magnetic field, B0. If you place it in an external magnetic field, this might acquire magnetization. Okay, magnetization is just the moment per unit volume. Okay, so if this material has magnets in them, those magnets might line up. And the field inside B, the material, oops. Okay, so here's the external field, here's the material that I was talking about while not showing you this. Because of the presence of this field, it will acquire, this material might line up the magnets, and the field inside is given by B. Okay, so the field inside is the external field plus mu naught times any magnetization the material acquires, or if it intrinsically had some. All right, so we define something called the magnetic field strength H, which is related to that. So we define B naught as mu naught times H. Okay. Just so H has the same dimensions as M. Okay. And so this is related to the external field, B naught. Okay. So the magnetization of the material is related to the external external magnetic field strength. And this proportionality constant is called the magnetic susceptibility. So essentially what this measures is how strong a magnet it becomes in the presence of an external magnetic field. Okay, so, and that can be a useful property. Okay, so here are some paramagnetic substances. They acquire magnetization in the direction of the external field, and there are their numbers, the susceptibility. Diamagnetic materials, on the other hand, acquire magnetization in the opposite direction, and their susceptibilities are negative. Okay. All right, so paramagnetic materials have small but positive magnetic susceptibility because of atoms with permanent moments. These moments are weakly interacting and in the absence of external field are randomly oriented. Okay. All right, so here's diamagnetism, which acquires an opposite moment. So what this is showing you is this is a frog that was frozen in water. Okay. I mean, they did it for the experiment. And water is diamagnetic material. And they put this in a strong magnetic field. So there's that block of ice. Here's this strong magnetic field, external magnetic field, B0. And remember, water is diamagnetic, so it acquires a magnetic moment like this. Okay. And this repels that. And so the force of gravity is being balanced by this repulsive force. And this frog is floating in air. Okay. So in water is diamagnetic, shown as a frog levitated due to a diamagnetic forces by a 16 Tesla field, a very strong magnetic field. By the way, I understand that after the experiment was done, they thawed the frog and it ran away. Superconductors are perfect diamagnets. So here's a magnet. So here's a magnetic field. And this is a superconducting material above the critical temperature. It's not a superconductor yet. And you cool it down, it becomes superconducting and it kicked out all the magnetic field. And so it's perfectly diamagnetic. All right, so that covers this chapter. Okay. Again, let me quickly summarize what we talked about. So what this chapter was about was currents producing magnetic fields. Okay, so moving charges producing magnetic fields. And so here was a moving charge and it produces magnetic fields like this. Okay. And the further out you are, the weaker the magnetic field. It does not produce any magnetic field. The magnetic field along the axial points are 0. Okay. This formula gives you the magnetic field from a moving charge of charge Q. Okay. The field strength falls off at 1/r². Okay. We saw that a current carrying conductor is a whole bunch of charges, and so the field due to each of those charges add up, and the field due to this current, due to a straight long wire, is the field lines are circular. The strength of the magnetic field is mu0 I divided by 2πa. And again, to get the direction of the magnetic field, what you do is use your right hand, stick your thumb out in the direction of the current, and your fingers point in the direction of the magnetic field. We saw that this is an electromagnet and its magnetic field is very similar to that of a bar magnet. We saw that two parallel wires carrying currents in the same direction attract each other. Currents carrying the same direction attract each other, and the force per unit length of the wire is equal to mu0 times the product of the currents divided by 2πa. If the currents are in the opposite direction, then they'll repel each other. And Ampere's law relates the line integral of the magnetic field around any closed loop to the current inside that loop. Okay. And this is similar to Gauss's law. All right, so that covers most of the topics. Here is a toroid. It's used in fusion reactions. And the magnetic field strength inside the toroid is strong, and it's mu0 n times I. It's related to the current. Okay. And the magnetic field around a straight solenoid is also given by mu naught Ni. And again, the field strength, the field inside a solenoid is large and outside is 0. All right, that covers the topics from this chapter. I will stop now and yield the floor to you guys.